People often believe that modern missile defense systems are designed to stop everything. That once a rocket is detected, it will almost certainly be intercepted, and that the sky above is constantly being controlled by precise and reliable technology. This belief is reinforced by visuals, by footage of interceptions lighting up the night, by statistics that suggest high success rates, and by the general idea that advanced systems like Iron Dome represent near-perfect protection. But this picture is incomplete because it ignores how these systems actually work under real conditions. And more importantly, what they are truly trying to solve. Missile defense is not about certainty. It is about probability. And that distinction is where most people misunderstand the entire system. Every interception attempt is essentially a race between two physical objects moving at extreme speeds, one trying to hit the other in a vast three-dimensional space. And even a small error in prediction can result in a complete miss. The system must first detect the incoming threat, then track it, then calculate its trajectory, and finally launch an interceptor that will collide with it at the right point in space and time. Each of these steps introduces uncertainty because the data is never perfect, the environment is never stable, and the situation is always changing. Radar signals can be affected by atmospheric conditions. Tracking algorithms rely on continuous updates, and the missile itself may not follow a perfectly predictable path. This means the system is constantly making adjustments, constantly refining its predictions, and constantly operating under pressure. What makes this even more difficult is that these decisions are being made in seconds, sometimes less, because the time between detection and impact can be very short. There is no room for hesitation, and there is no opportunity to correct mistakes once the interceptor is launched. Now consider what this means in practice. Because even if the system has a high success rate, say 90% or higher, that still implies that some threats will not be intercepted. And in everyday situations, a 90% success rate might sound impressive, but in missile defense, it is not enough because the consequences of failure are extremely high. The attacker only needs one missile to reach its target to cause damage, while the defender must stop every single one to maintain the illusion of complete protection. This creates a fundamental asymmetry that cannot be eliminated by technology alone. The defense system is always playing a more difficult game because it must perform perfectly under imperfect conditions. It must succeed repeatedly without error, while the attacker only needs a single moment of success. And this is the key point that is often overlooked. Missile defense systems are not designed to be perfect. They are designed to reduce risk, to lower the number of successful hits, and to buy time. But they cannot guarantee absolute protection. Once you understand this, the expectation changes. Because the question is no longer why some missiles get through. The real question is how the system manages to stop as many as it does despite the inherent limitations of physics. The idea of perfect defense is not just unrealistic, it is physically impossible because the system is constrained by time, by information, and by the fundamental unpredictability of real-world conditions. And this is where the story truly begins. Not with failure, but with the realization that perfection was never part of the design in the first place. What makes the problem even more challenging is that sometimes the system is not even dealing with a single target in the first place. What appears as one missile on radar can suddenly transform into many independent objects. And this transformation happens very quickly, often within seconds, leaving the defense system with almost no time to adapt. This is because certain missiles are designed with cluster warheads, which means instead of carrying one large payload, they carry multiple smaller submunitions that are released during the final phase of flight. From a simple perspective, it may still look like one launch, one trajectory, one threat. But from a physics standpoint, the situation has already changed into something far more complex. The moment the warhead separates, each submunition becomes its own object, governed by its own motion, influenced by its own velocity, angle, and interaction with the atmosphere. This means the system is no longer solving a single interception problem. It is now solving many simultaneous problems, each one requiring its own prediction and its own response. And because these objects are released at high speed and high altitude, even small differences in their initial conditions can lead to large separations as they descend, spreading them over a wide area and increasing the difficulty of interception. The defense system must now detect and track each of these objects individually. But the challenge does not stop there, because not every object behaves in a predictable way. Some may slow down differently due to air resistance. Some may tumble, and some may even be designed to mimic real warheads. Creating additional confusion, this introduces a layer of ambiguity that forces the system to make rapid decisions without complete certainty. It must determine which objects are actual threats and which ones are not. But it must do so in a very limited amount of time, often just seconds. This creates a difficult trade-off, because if the system chooses to engage every object, it risks exhausting its interceptors very quickly. And interceptors are not unlimited. Each one is a physical resource that takes time and energy to deploy. On the other hand, if the system tries to prioritize and ignore some objects, it risks allowing a real warhead to pass through. This is where the strategy of the attacker becomes clear. The goal is not just to deliver a payload, but to multiply the number of decisions the defender must make, to increase complexity, and to stretch the system beyond its optimal capacity. One missile becomes a network of problems, each one competing for attention, each one demanding a response, and all of them arriving within a narrow window of time. From the outside, but it may still look like a single event. But inside the system, it is a rapidly expanding scenario where uncertainty grows with every second. The defense is no longer focused on a single point in space. It is forced to manage an entire region, tracking multiple trajectories, predicting multiple outcomes, and allocating limited resources across many simultaneous threats. This transformation from a single target to many targets is not just a technical detail. It is a fundamental shift in how the problem is defined, because once complexity reaches a certain level, the difficulty is no longer about precision. It is about capacity, and capacity, unlike precision, has limits that cannot be easily overcome, especially under time pressure. This is why a single missile, when designed in this way, can challenge even the most advanced defense systems, not by being unstoppable on its own, but by turning a simple problem into a system-level challenge that is far harder to solve in real time. Even if the system could perfectly identify every object and track every fragment, there is still a deeper limitation that cannot be removed, and that limitation is time. Modern missiles travel at extraordinary speeds, often several kilometers per second, which means that the distance between launch and impact is covered in just a few minutes, sometimes even less, depending on the range. From the moment a missile is detected, the system enters a race against the clock, and every step in that process consumes time that cannot be recovered. First, the sensors must confirm that what they are seeing is real. Then the system must calculate a trajectory, predict the point of impact, decide whether the object poses a threat, and finally launch an interceptor that must travel its own path to meet the target at precisely the right moment. Each of these steps may only take fractions of a second, but together they form a chain. And any delay anywhere in that chain reduces the total time available for interception. The critical detail here is that the missile is not slowing down. It is continuously moving closer, continuously reducing the space in which the defender can act. This creates a situation where even a perfectly functioning system is under constant pressure, because it is always reacting, never initiating. And reaction, by its nature, is always behind the event it is trying to control. Now consider the physics of interception itself, because hitting a missile at these speeds is not like aiming at a stationary target. It is more like predicting where two extremely fast objects will intersect in space, both moving under dynamic conditions. The interceptor must be launched toward a point that does not yet exist, a future position based on calculations that must account for velocity, direction, atmospheric drag, and possible changes in motion. If the incoming missile maintains a stable path, this prediction is difficult but manageable. But if the missile changes even slightly, if it maneuvers or if external factors alter its motion, then the prediction must be updated in real time. And that requires additional computation and additional time. And time, in this context, is the one resource that cannot be increased. This is why speed is not just an advantage for the attacker. It is a form of pressure applied to the entire system, forcing it to operate closer and closer to its limits. As the available time window shrinks, the margin for error also shrinks. And what might have been a small mistake under slower conditions becomes a critical failure at higher speeds. There is also a physical constraint on the interceptor itself, because it cannot instantly reach the target. It must accelerate, travel, and adjust its course, all while the incoming missile continues its descent. This means that the system must act early, often before it has complete information. And this introduces another layer of uncertainty. Acting too late means there is no time left to intercept, but acting too early means committing resources based on incomplete data. This balance between speed and decision-making is at the heart of the problem, and it reveals something fundamental about modern missile defense. The system is not failing because it cannot see or because it cannot calculate. It is constrained because it cannot escape the flow of time. Everything it does is bound by the sequence of events: detection, decision, interception. And each step consumes a portion of a limited window that is constantly closing. The attacker, on the other hand, only needs to maintain that pressure, only needs to ensure that the system is always reacting, always slightly behind, always operating under conditions where perfection becomes increasingly difficult. And this is where the deeper truth emerges. The challenge is not just about speed itself. It is about the relationship between speed and response. Because as speed increases, the system does not simply need to react faster, it needs to react with less information, less certainty, and less room for correction. And that is a problem that no amount of technology can fully solve, because it is rooted in the fundamental structure of time and motion. even if the system could somehow keep up with the speed and manage the time pressure, there is another layer of difficulty that changes the problem entirely, and that is unpredictability. Many people imagine missiles following a smooth and simple arc, like a projectile moving in a clean parabolic path, something that can be calculated once and predicted with high accuracy. But modern missiles are not limited to that kind of motion anymore. Some of them are designed to maneuver during flight, especially in the final phase. And this is where the problem becomes far more complex. Instead of following a fixed trajectory, the missile can adjust its path, changing direction slightly or even aggressively, making it much harder for the defense system to predict where it will be in the next moment. From a physics perspective, this introduces a dynamic element into what was previously a relatively stable calculation. The system is no longer solving a single trajectory problem. It is now solving a continuously changing one, where every new movement requires an updated prediction. And these changes do not need to be large to have a significant effect. Even a small deviation at high speed can result in a large positional difference over distance, which means that an interceptor aiming for a predicted point can easily miss if that prediction becomes outdated. This is why these types of missiles are sometimes described as moving in a way that appears irregular or even unpredictable. Because from the perspective of the tracking system, the target is not behaving like a simple object governed by a fixed path. It is behaving like a system that is actively resisting prediction. Now consider what this means for interception, because the interceptor itself is also following a calculated path. It is launched toward a future position based on current data. But if the target changes its motion after that calculation, then the interceptor must adjust as well. This requires continuous guidance, constant updates, and extremely fast response times, all while both objects are moving at very high speeds. The problem is not just about following the target. It is about anticipating its future behavior in an environment where that behavior can change at any moment. This creates a situation where the defense system is always slightly behind, always reacting to changes that have already occurred, rather than predicting a stable future. And as the time window shrinks, there is less opportunity to correct these errors, which increases the chance of a miss. There is also an energy aspect to this, because maneuvering at high speed requires control surfaces or thrust vectoring, which means the missile is actively using energy to alter its path. And this allows it to create movement patterns that are difficult to model with simple equations. For the defense system, this adds another layer of uncertainty, because it must consider not just where the missile is, but what it might do next. And this is fundamentally different from tracking a non-maneuvering object, where the future can be estimated with relatively high confidence. Here, the future is fluid. It is constantly being rewritten by the motion of the missile itself. What appears from the outside as a small adjustment in direction is, in reality, a disruption of the entire prediction process. And when you combine this with the already limited time available and the complexity introduced by multiple targets, the difficulty increases dramatically. The defense system is no longer solving a precise mathematical problem. It is dealing with a moving uncertainty, a target that does not simply follow the rules but actively challenges them. And this is why maneuvering missiles are so difficult to intercept. Not because they are invisible, not because they are infinitely fast, but because they undermine the very foundation of prediction, turning a calculable path into a constantly shifting problem that must be solved in real time with limited information and limited time, even if the system could track maneuvering targets and adapt to their unpredictable motion, there is still another transformation that makes the problem even more difficult. And that transformation happens at the boundary between space and the atmosphere. Many modern missiles do not behave as a single object throughout their entire flight. Instead, they separate into different components during the mid-course phase, often outside the atmosphere, where conditions are very different from what most people imagine. In that environment, there is almost no air resistance, which means objects can travel in smooth paths with minimal disturbance. And multiple components can move together in ways that appear clean and predictable. At this stage, the system may see what looks like a stable set of objects moving in a consistent pattern, and it can begin to calculate trajectories based on that information. But this is where the illusion begins, because what happens next changes everything. As these objects re-enter the atmosphere, they encounter air again, and that interaction introduces forces that were not present before. Drag, heating, and a turbulence, and small variations in shape and mass begin to affect each object differently. What was once a clean and predictable motion in space becomes a complex and chaotic behavior in the atmosphere. Some objects slow down more than others. Some experience slight deviations, and some may even be designed to change their path during re-entry. Adding another layer of uncertainty, from the perspective of the defense system, this is a critical moment, because the predictions made earlier are now being disrupted by new forces, and the system must rapidly update its understanding of where each object is going. But there is very little time to do this, because re-entry happens at extremely high speed, and the distance to the target is shrinking quickly. This creates a situation where the system is forced to reconcile two different realities: the clean, predictable motion it observed in space, and the messy, unpredictable motion it now sees in the atmosphere. And this transition is not smooth. It is abrupt, which makes it difficult to maintain accurate tracking. There is also the issue of discrimination, because not all objects behave the same way during re-entry. Some may be actual warheads, while others may be decoys or fragments designed to mimic real threats. The system must determine which objects are dangerous based on how they move under atmospheric conditions. But this requires interpreting subtle differences in behavior, differences that may not be clear or consistent. At the same time, the heat generated during re-entry can affect sensor readings, creating additional noise and reducing the clarity of the data. This means that the system is making critical decisions under conditions that are both time-constrained and information-limited. What makes this even more challenging is that the attacker can design these systems to exploit this transition, to create confusion exactly at the point where the defense is most vulnerable, by controlling how and when components separate and how they behave during re-entry. The attacker can increase uncertainty and force the system to deal with multiple possibilities at once. From a physics standpoint, this is not about breaking the rules. It is about using the rules in a way that maximizes complexity. The motion of each object still follows physical laws, but the combination of many objects, each interacting with the atmosphere in slightly different ways, creates a situation that is extremely difficult to predict with high accuracy. And because the system must act quickly, it cannot wait for perfect information. It must make decisions based on incomplete and rapidly changing data. This is why the transition from space to atmosphere is so critical. It is not just a change in environment. It is a point where predictability breaks down and uncertainty increases sharply. The system is no longer dealing with a clear picture. It is dealing with an evolving scenario where previous assumptions may no longer hold. And in that moment, even a small error in interpretation can lead to a missed interception. Not because the system failed to act, but because the situation itself became too complex to resolve perfectly within the available time. Even if the system could track multiple objects, adapt to maneuvering targets, and adjust for the chaos of re-entry, there is still a final limitation that cannot be avoided. And that limitation is capacity. Every defense system, no matter how advanced, operates with finite resources, finite sensors, finite processing power, and most importantly, a finite number of interceptors that can be launched within a given time window. This means that beyond a certain point, the problem is no longer about precision or prediction. It becomes a question of how much the system can handle at once. This is what is known as saturation. A situation where the number of incoming threats exceeds the system's ability to respond effectively. From the outside, it may look like a large attack, multiple missiles launched at the same time. But from the inside, it is something more critical. It is a rapid accumulation of tasks that must all be solved simultaneously, each one demanding attention, each one competing for limited resources. The system must detect, track, classify, and assign interceptors to each object, but it cannot do all of this infinitely fast. And it cannot launch unlimited interceptors at once. There are physical and operational limits on how quickly interceptors can be prepared, launched, and guided, and these limits define the maximum capacity of the system. Once the number of incoming objects approaches or exceeds this capacity, the system begins to degrade. Not because it stops working, but because it is forced to prioritize. Some targets are engaged, others are delayed, and some may not be engaged at all. This is where the attacker gains a significant advantage, because the goal is no longer just to deliver a payload. The goal is to push the system into a state where it cannot respond to everything at once. And this can be achieved not only by increasing the number of missiles, but also by increasing complexity, by combining multiple types of threats, maneuvering objects, decoys, and cluster effects, all arriving within a narrow time window. From a physics and systems perspective, this creates a bottleneck, a point where the flow of incoming threats exceeds the flow of defensive responses. And once this bottleneck forms, the outcome is no longer determined by accuracy alone. It is determined by throughput, by how many problems the system can solve per unit of time. This is a fundamentally different type of challenge, because improving accuracy does not solve a capacity problem. And increasing speed does not eliminate the limits of resources. The system is constrained by the rate at which it can process information and act on it. And that rate cannot be increased indefinitely. There is also an economic dimension to this, because interceptors are expensive, and using multiple interceptors for a single target increases the probability of success. But it also consumes resources more quickly, which can accelerate the onset of saturation. This creates a strategic dilemma, whether to conserve resources and risk failure, or to expend resources aggressively and risk depletion. And this dilemma is exactly what the attacker is exploiting. By creating scenarios where the defender is forced into difficult decisions under pressure. From the outside, it may appear that the system is failing when some objects get through, but in reality, the system is operating within its limits, limits that are defined not by design flaws, but by the fundamental constraints of physics and engineering. Saturation is not a bug in the system. It is an inevitable consequence of finite capacity in the face of increasing complexity and speed. And once the system reaches that point, even a small additional load can have a disproportionate effect, pushing it from effective defense into partial failure. This is why modern attacks are often designed not just for impact, but for overload. Because once the system is overwhelmed, the probability of something getting through increases dramatically. Not because the system cannot function, but because it cannot function perfectly under those conditions. When you put all of this together, the detection uncertainty, the multiplication of targets, the extreme speed, the unpredictable motion, the chaos of re-entry, and the limits of system capacity, you begin to see a pattern that is easy to miss if you only look at individual pieces. Each part on its own can be understood. Each problem can be studied and improved. But when they are combined, they create a system-level challenge that is fundamentally constrained by physics. This is why the question is often misunderstood. People ask why some missiles get through, as if it is a failure that needs to be fixed. But the deeper answer is that under these conditions, complete interception was never physically guaranteed in the first place. The system is not designed to eliminate risk entirely. It is designed to reduce it as much as possible within the limits of time, information, and resources. And those limits are not arbitrary. They are built into the nature of how objects move, how information is gathered, and how decisions are made in real time. What makes modern missile systems so difficult to stop is not a single breakthrough or a single technology. It is the way multiple physical effects are layered together, each one increasing complexity, each one reducing certainty, and each one compressing the time available for action. The defender is not solving one problem. It is solving many problems at once, under conditions where perfect information is impossible and perfect timing is unattainable. And this leads to a fundamental asymmetry that cannot be removed. The attacker only needs one successful path through the system, one sequence of events where everything aligns just enough to allow a missile to reach its target, while the defender must prevent every possible path, every possible variation, every possible outcome from a mathematical perspective. This is the difference between needing one success and needing zero failures. And that difference becomes overwhelming as complexity increases. Even if the system is extremely effective, even if it stops the vast majority of incoming threats, the probability of a single failure never disappears completely. And that small probability is enough to define the outcome. This is why the problem is not simply technological. It is structural. It is rooted in the relationship between offense and defense, between action and reaction, between prediction and uncertainty. The defense system is always responding to events that have already begun, always operating within a shrinking window of time, always making decisions based on incomplete data, while the attacker is free to design scenarios that maximize pressure, maximize complexity, and exploit every limitation in the system. And when all of these factors are combined, the result is not a system that fails, but a system that operates at the edge of what is physically possible. This is the reality that is often hidden behind simplified explanations The idea that technology alone can create perfect protection, when in fact the deeper truth is that physics sets boundaries that cannot be crossed. No matter how advanced the system becomes, it will always be constrained by time, by energy, by information, and by the inherent unpredictability of real-world conditions. And once you understand this, the question changes completely. It is no longer about why interception is not perfect. It is about how close the system can come to perfection, despite the fact that perfection itself is not achievable. In modern warfare, the outcome is not decided by who has flawless systems. It is decided by who can operate more effectively within these limits, who can manage uncertainty better, and who can push the balance just far enough in their favor. And in the end, what appears to be a technological contest is, at its core, a demonstration of something much deeper, the quiet but unavoidable influence of physics, shaping what is possible and what is not.